Right, there we go. Well, over to you, Franz. So Franz is going to tell us about verification of CHERI C++ programs. Over to you. Thank you.
Yes, I'm Franz Brausse. I'm presenting work here together with my colleagues that we mostly performed in Manchester, but we have a few colleagues working on ESBMC abroad. So this is a two-words talk, right? The title says two words. This is work in progress. It's not finished, but we have identified a few issues we did run into, and we also have a few takeaways, basically. So I should talk about ESBMC first, because the tool is probably not known. It's a verifier for C and C++ and a few other languages. Then I would like to introduce the changes that we had to make in order to support CHERI C as a new C dialect, and basically the challenges we faced with this. So ESBMC itself is, it's a logic-based automated reasoning tool. As it says here, the input is a program and the output is a verification result, either successful, that means all the properties that we check by default are satisfied, or we find a failure, in which case we also produce a witness, which is a trace of assignments to the variables in the program that leads to the violation of the property. It's an open source project. It's based on, so the core concept is symbolic execution. We've heard this a few times mentioned today. It has a quite optimized, I would say, implementation of the symbolic execution, and it is augmented also with techniques like k-induction in order to reason about not just a bounded initial trace of the program, but also to reason about loops in particular. Features concurrency support and has, as I said, support for a few different input languages, but we focus on C and C++. So this is part of the DSBD project. This has sponsored the extension to CHERI C as an input language. And what we had to do with for that, I want to sketch here. So this is the way it works. We start with a given user program. We need the source code. Then we run it through the Clang front end and derive the AST. And that is where Clang stops. So we use the AST to transform it into our own intermediate representation, which is called Go2. It's a very simple intermediate language that has basically imperative assignments and jumps. Then we have models for the external libraries. This could be the C library with functions like malloc and so forth. But we also support pthreads as an external library and a few others. And then the internal representation is executed by the symbolic execution engine and eventually transformed into an SMT formula, and then we support multiple solvers for this. Interestingly, the best is still Bulector, even it's quite old now. Okay, and the result of this will be either the correctness proof or the violation proof. So what did we have to do in order to support CHERI C? We could obviously replace the front end with the CHERI enabled C-lang, which has been very easy to do, so that was good. The ASTs are mostly compatible. Then we want to model the CHERI C API, that is the intrinsics that basically allow to modify the capabilities and to inspect them and so forth. And then we had to implement the memory model, and that means basically we had to make a decision. Do we want to check for all the things that the hardware is actually supposed to do, or do we assume these things? And the tag memory obviously is a concept that was new to our previous work, and we had to model it in some way, so it's not addressable, and this is a problem because there are a few features of ESBMC that run through the program and create new instructions, new kinds of expressions, and they could, in principle, also create address of expressions. They mustn't be allowed on the tags, right? So that is a problem we faced. The goal was here to support both the interpreting the program as an uncompressed and a compressed capability in hybrid and pure cap mode. And this was basically already done for us by the Clang development. So we get the correct AST in any of these nodes. Yeah, since this is for user-space programs mostly, we need an execution environment, and CHERI PSD1 worked quite well for that. And here begin the challenges that we ran into. So the compression algorithm is not trivial, and to symbolically encode it every time a capability is modified is too much. So that means the SMT formula explodes basically, and yeah, this will not work. So we tried this, it doesn't work. So what we do instead now is first aggressively reduce the number of invocations of this compression algorithm. And if we do, then we do it purely on the SMT level. So that means it will be a symbolic address all the way through the to the SMT formula. This performs a bit better. Sorry, I don't have numbers right now, but this is still in development. And this is the two directions that I mentioned earlier. So we have the option to either assume or to prove the additional hardware guarantees that CHERI offers. And it turns out that proving the absence of any CHERI exceptions, this is also very costly in terms of time. Maybe to give a rough number, so there are programs that we can prove correct or find a violation in a few seconds, and others take like hours, days, or, well, never stop. And all of these numbers will go up if we prove that there will be no CHERI exceptions. On the other hand, if we assume that, this brings verification time down a lot, so this increases performance, but it also allows us to start reasoning about functions where we don't have source code for. So external library functions without a model. Because on a CHERI architecture, we can assume that this function only touches certain parts of memory that are given to it by accessibility. Right. Yeah, we can optimize a few operational models as well. This brings more performance if we assume that. So these are the two directions we implement. And there are some more challenges. This is also the last one I'm going to talk about today. And this is for pointer provenance. And so I have two examples here that come from the so-called real world. One is competition on software verification as VComp. It's pretty big. So this is an example where we allocate memory dynamically, store the address, free it, allocate again, and compare the addresses. So the first program should fail. And I believe, after listening to Priya's talk, that the equal operator will fix this now for us. But yeah, so it should basically be possible for malloc to return the same memory twice. This is one example. And the second example comes from ARM. So they have this confidential compute architecture, and a part of that is called RMM. And this is basically a VM that runs firmware, and this is a reduced example from ARM's firmware for this RMM. And they expect this to work. So what does it do? Take a buffer, take some unknown address, I. Assume that I is between the buffer, so in the range of the buffer, and then basically derive a pointer into this buffer from the distance between, so I and the buffer itself, and the reference step. Yes, and so here the question is, should this work and why doesn't it? So they expect this to work because the buffer, the first one, this one here, should carry along the provenance. It's not clear whether it does. All right. So as a takeaway, replacing the front end itself was easy to do. That was good. The tagged memory and the Cherry C API weren't too hard to implement. Though I should say this is not 100% working yet. The tagged memory, we have some issues with local variables on the stack because they are modeled differently. Provenance is an issue because there are these software competitions that claim to use real-world programs as part of their benchmark set, and they are not compatible with this expectation that provenance matters. Another takeaway, the in-memory representation is very difficult to reason about on a symbolic level, especially when it's compressed. But assuming Cherry semantics does help with the performance and complexity of software verification.
Thank you. Well, thank you very much. I'm particularly intrigued by the last point. Robert.
I was going to ask about the last point. If we wanted to go from a sort of slightly hand-wavy statement at that front to a sort of more empirical, larger-scale study, how would you approach that in terms of arguing that Cherry semantics does in fact help with verification? I mean, it's like an intriguing claim, very nice if true, but I wonder how do we even test that?
Well, we do run our software on, for instance, the ESB benchmark sets. This is an extensive suite of programs. They are not Cherry aware at all, so our thought was, okay, let's interpret them as POCL programs and see what happens. So how is the performance on the one hand side, but also how many tests fail their verdict. So that would be the first approach, I think. We have a bunch of Morello boards in Manchester, and you could even run those programs there to see.
I think that would be very interesting. Ian.
Thank you. That was really interesting to see. I want to open up the point about provenance in your third one, saying that different people have different ideas, and in particular the competition examples. Mm-hmm. So the first one should fail, the second one should work. Can you tell us what happens on Morello in your tester, and just expand again, I know you tried this already, why people think one should fail and one should work? What are they expecting to happen and what does happen?
So the first one is, my assumption is that the first one has been crafted with model checkers in mind. So this is something they usually fail to do, even though it is possible that the address returned by malloc is the same after delivery. Right? So if it's the same, then this will fail. This assertion will fire, and this can happen.
So it happens in practice, but many model checkers would not realize this. Okay.
Exactly, yes. And the reason is that basically for each malloc they create a new symbol, and different symbols shouldn't overlap in the address space.
And you think that for Cherry, it's still the case that should fail because you could get an exactly identical pointer?
Well, for the same n, yes, but if we modify the n to an m, then the bounds would differ. But I've just heard that currently the equals will fix that, so I wasn't aware of that.
Okay. And the second one, do you think that shouldn't work? That looked to me like it's something that does mess around with capabilities and pointers, but it should do so in a safe way.
Why do you think this is safe?
Because the provenance for the buffer will count. The provenance will, even in the default Cherry Clang compiler, will pick up provenance from the buffer, and that indeed has access to that relevant part.
So how does Clang treat this undefined behavior here? I mean, it's implementation defined. The class to chart is implementation defined, but
oh, yeah, so that's a null-derived pointer,
okay.
and it will do some arithmetic with that, and it'll get an integer, but the compiler will construct the pointer for the Q by taking the buffer and adding an offset.
And that's dependent on the order of the...
So if you did it the other way around, the compiler might decide that's obviously the wrong one to take, or it might issue a warning, or if you put it through Irina's checker, static analyzer, it will give an explanation that says, well, this one here is going to be null derived. You shouldn't use that as a pointer, but you could use that one there.
Right.
And then maybe suggest some casts.
But then in summary, I would say that the decision to use the left operand to derive provenance from was right for ARM's code.
So in this case, the right-hand side is a fraction of...
In this case, the right-hand side of the plus is a subtraction of 2 pointers, and that should always be a nice integer with no provenance. So I think this is not a complicated example, unless do I have that wrong?
Well, there are some subtleties to this example. Completely unrelated to CHERI if we get into the ISOC semantics, but to clarify, the left-hand side thing for binary operators is specifically if you're doing an arithmetic operation on an int pointer t value. If you're doing it on a standard pointer, ISOC says that one of the operands is a pointer, one of them is an integer, and you always take the provenance of the pointer. That one is completely unambiguous, and you can swap the arguments around however you like, and that's completely always going to be that the pointer is the one that takes the provenance and the integer isn't. So in this case, buffer will always be the pointer. If you swap and buffer would still be the pointer. It's only when you have int pointer t, because you're doing an arithmetic operation on an integer, and integer operations are defined that both operands have to be the same type, which is where the ambiguity comes from, versus pointers where one is a pointer, one is an integer. An int pointer t historically was just a long, so it didn't matter. Now it's a capability that's masquerading as an integer. You have some a bit of a mismatch there that is where that complexity comes from. In terms of this being well defined or not, it really depends on what non-det is doing and what your interpretation of provenance is for int pointer t. Right, and that will still depend on interpretations of the standard, I think, because the standard is very clear that if you do subtraction of pointers to different objects, that's undefined. If you do comparison between different objects, etc., that's undefined behavior. But you're dealing with int pointer t, which is historically something that compilers kind of, well, the standard doesn't really talk about provenance for int pointer t properly. So I think the answer to this is nobody knows what this does because C doesn't tell you what it does. And that maybe PNVI ADUDI will tell you what it does. Hopefully it does, but I couldn't tell you what it tells you it does either. But it has nothing to do with CHERI. CHERI doesn't care what that is. It will behave the same.
If I may, we don't attach provenance to in PTRT, only to the actual pointers. So there will be no provenance in PTRT here.
I'm going to give Peter Sewell the last question.
So a different kind of question. So I didn't really understand from the talk, beyond the competition examples, what kind of example do you think you can reasonably aim to be able to do verification or anti-verification of? What sort of scale is this supposed to work at?
So you mean the complexity of the input programs?
Yeah.
Well, it's hard to explain in like lines of code terms. Yeah. It's really the inherent complexity of the algorithm that's implemented. So far we have a few Linux drivers, so drivers from the kernel which have been made into a program to check a few properties, so they can be verified. We do verify small pieces of code, like, Bash itself would, for instance, be too much already to get reasonable performance for all the properties that we usually check for, which is undefined behavior and these kinds of things. Yeah. So maybe I can just repeat what I said earlier. We would start basically with the benchmark set that we have from SBCom and see whether that already with the CHERI, additional CHERI checks that we need to do, what's the difference in performance. So that's the way forward.
Yeah. Okay, thanks.
Great. I think we should wrap up there. Thank you very much.